Have you ever stood by the ocean and watched the waves roll in and out? Usually they are pretty gentle, a rhythmic sound that can lull you to sleep. But imagine a wave that isn't gentle at all. Imagine a wave as tall as a building, moving faster than a jet plane. That, my friends, is a tsunami. The word tsunami comes from Japanese. Isu means harbor, nami means wave. So it literally means harbor wave. These are not your everyday fun for surfing waves. They are powerful, destructive forces of nature that can change coastlines and affect lives in a matter of minutes. Understanding them is not just cool science, it's incredibly important for staying safe. A tsunami is often called a tidal wave, but that's not quite right. Tides are caused by the gravitational pull of the moon and the sun, creating a predictable rise and fall of the sea level. Tsunamis, on the other hand, are something else entirely. Think of it like this. If you gently swish your hand in a bathtub, you make little ripples. But if you suddenly drop a big brick into the tub, you create a huge splash that sends water sloshing over the sides. A tsunami is like that giant splash, but on a planetary scale, involving the entire depth of the ocean. These gigantic waves are born from some of the most powerful events on our planet. To understand how a tsunami begins, we first need to look deep down, far below the ocean floor. Our planet Earth isn't one solid ball of rock. Its outer layer, called the crust, is broken up into giant, irregularly shaped pieces, kind of like a cracked eggshell or a massive jigsaw puzzle. These giant puzzle pieces are called tectonic plates. They are enormous slabs of rock that float on a hotter, softer layer of rock beneath them called the mantle. These plates are constantly on the move, drifting around the globe at about the same speed your fingernails grow. That might not sound very fast, but over millions of years this slow, steady movement has shaped our world, creating mountains and oceans. There are about a dozen major tectonic plates and many smaller plates all bumping and grinding against each other. These meeting points are called plate boundaries, and they are where most of the action on our planet happens. When two plates meet, different things can happen. They slide past one another, they pull apart from each other, and sometimes they collide head-on. The most important interaction for our tsunami story is when one plate is forced to slide underneath another. This process is called subduction, and it's like one giant plate taking a nosedive beneath its neighbor. This doesn't happen smoothly. It's a jerky, friction-filled process. The immense friction between these grinding plates causes stress to build up over years, decades, or even centuries. The rocks at the plate boundary are locked together, but the rest of the plates keep moving, storing up an incredible amount of energy like a stretched rubber band. When the stress finally becomes too much for the rocks to handle, they snap and shift with incredible force. This sudden release of energy is what we feel on the surface as an earthquake. And when this happens under the ocean, it sets the stage for a truly spectacular and dangerous event. Now that we know about our planet's tectonic plates, let's connect them to tsunamis. The vast majority of tsunamis, more than 80%, are caused by powerful earthquakes on the ocean floor. These are typically megathrust earthquakes. A megathrust occurs at a subduction zone, where one tectonic plate slides under another. These plates don't slide smoothly, they get stuck, and pressure builds. Over years, the overlying plate bends downward, squeezed like a giant ruler pushed at one end. When the pressure becomes too great, the stuck section suddenly breaks free and lurches forward. That sudden, violent movement is the earthquake. The bent overlying plate snaps back upwards with tremendous force. This abrupt movement can happen over hundreds of kilometers of seafloor. Imagine all the water sitting on top of that. The whole column of water, seafloor to surface, is shoved upward. This is when a tsunami is born. It's not a surface splash. It's the entire ocean depth getting pushed. That initial push creates a series of waves that travel outwards in all directions from the epicenter. In the deep ocean, these waves may be only a meter high or less. They're often undetectable to ships, but they are extremely long, hundreds of kilometers between crests, and they move incredibly fast. Tsunamis can travel over 800 kilometers per hour, as fast as a commercial jet airplane. The energy moves through the water, a silent, speedy messenger. Danger starts when the wave approaches land. Near the coast, the wave slows due to seabed friction. All that energy has to go somewhere. As the wave slows, its height grows dramatically. The front slows more than the back, so water piles up. A 1-meter deep ocean wave can transform into a monstrous wall of water, 10 meters tall, 20 meters tall, or even 30 meters tall, ready to crash ashore with unimaginable force. Let's visualize the immense scale of this event. An underwater earthquake that can trigger a tsunami is not a small tremor. It's a catastrophic rupture of the Earth's crust. Imagine a section of the seafloor the size of a large city, or even a small state suddenly jumping upwards by several meters in seconds. This vertical displacement acts like a giant paddle, pushing the entire water column above it upwards. A mound of water forms at the surface, then collapses, sending waves radiating outwards. Not like wind waves. Wind only moves the surface layer. A key factor is the type of fault movement. Vertical movement is the most dangerous for tsunamis, where the seafloor is pushed up or dropped down. Sometimes the first sign at the coast is not a wave but a sudden retreat. The ocean can drain away, exposing the seabed, reefs, fish. This drawdown happens if the trough reaches the shore first. It's deceptive and dangerous. People may walk out onto the exposed seafloor. But it's a critical warning. The crest often follows minutes later with devastating force. A tsunami's power is almost impossible to grasp. It's a turbulent surge filled with debris, cars, trees, parts of buildings. Force depends on water speed and height. A cubic meter of water weighs about a ton, and tsunamis can deliver millions of tons onto a coast. They obliterate structures. The long wavelength keeps the surge coming, flooding inland for minutes, then dragging everything back out to sea. While earthquakes are the leading cause of tsunamis, they aren't the only one. Our planet has another powerful geological force that can make a big splash: volcanoes. When a volcano erupts on land, we see ash clouds, lava flows. Many of the world's most active volcanoes are hidden deep beneath the ocean's surface. Submarine eruptions can blast apart rock, send superheated gas, send magma shooting upwards. A violent explosion pushes water aside, displacing it and creating tsunami waves that radiate outward. Famous example, Krakatoa, Indonesia, 1883, island volcano, not fully submerged. The eruption collapsed in on itself, forming a caldera. The collapse displaced massive seawater, generating waves over 40 meters high. Those waves crossed the Indian Ocean, effects detected as far as the English Channel. Eruptions can trigger tsunamis in several ways: explosive displacement of water, collapse above water, collapse below water, massive landslides, pyroclastic flows, superheated hot gas, ash, rock, can race into the sea at high speed, displacing water and generating a tsunami. Volcanic tsunamis are harder to predict. Warning systems rely on seismic earthquake signals. Volcanic eruptions may lack clear seismic signatures, so warnings can be delayed or missed. Coastal communities near active volcanoes face localized, sudden threats. Ongoing research helps us understand and prepare for these fiery, watery threats. Consider it. Beyond earthquakes and volcanoes, there is another significant cause of tsunamis: landslides. These can happen above the water or below the water. Imagine a massive chunk of a coastal cliff, weakened by heavy rain or a small earthquake, suddenly breaking free and crashing into the sea. This sudden dumping of millions of tons of rock and soil into the water acts like a giant paddle, displacing a huge volume of water. One extreme example happened in Lituya Bay, Alaska, in 1958. An earthquake along a nearby fault triggered a colossal rock slide, causing an estimated 30 million cubic meters of rock to fall into the narrow bay. The resulting splash created a mega tsunami that surged up the opposite side of the bay to a height of 524 meters, taller than the Empire State Building. While this was very localized due to the bay's unique shape, it stands as a powerful reminder of the immense wave-generating potential of a massive landslide. Underwater landslides can also be a major cause of tsunamis. These are often triggered by earthquakes, which shake the unstable sediment that is built up on steep continental slopes. The shaking can cause huge sections of the seafloor to slump or slide downhill in a powerful, fast-moving underwater avalanche called a turbidity current. That sudden movement of massive material displaces the water above it, creating tsunami waves that can travel great distances and threaten distant coastlines. Scientists study the seafloor to identify areas of unstable sediment that could pose a future tsunami risk. Finally, though extremely rare, even extraterrestrial objects can cause tsunamis. A large asteroid impacting the ocean would release an incredible amount of energy. The impact would create a massive crater and displace a colossal amount of water, generating a mega tsunami that could devastate coastlines across the entire globe. While the probability of such an event is very low, scientists study ancient impact craters to understand the potential consequences. It shows that the forces that create tsunamis can come not only from deep within the Earth but also from the vastness of space. So, we've journeyed deep beneath the waves and into the Earth's crust. We've seen how the slow dance of tectonic plates can lead to a sudden violent snap, releasing energy that travels across oceans at the speed of a jet. We've explored fiery underwater volcanoes and colossal landslides, all of which have the power to create one of nature's most formidable forces, the tsunami. Understanding this science isn't just a cool mental exercise, it is absolutely vital. It's the foundation upon which our entire system of safety and preparedness is built. Knowing how tsunamis happen, knowing where tsunamis happen, knowing why tsunamis happen, this scientific knowledge allows us to build incredible early warning systems. Organizations like the Pacific Tsunami Warning Center use a global network of seismometers. When a powerful underwater quake is detected, they run computer models to predict a tsunami and its path. Buoys in the deep ocean, dart buoys, measure passing waves and confirm a tsunami. That data is used to issue warnings to coastal communities, sometimes giving them hours to evacuate. Education is just as critical as technology. A strong earthquake that makes it hard to stand, the sudden strange retreat of the ocean. People who recognize these signs act immediately and move to higher ground. Knowledge passed down and taught in schools empowers life-saving decisions. Signs showing tsunami evacuation routes and designated safe zones are a direct result of our scientific understanding of how far inland these waves can travel. Ultimately, science gives us the power of prediction and preparation. By studying our planet, we learn respect without living in fear. We build resilient communities with ingenuity and understanding. From a tiny crack in the seafloor to a wave that can cross an ocean, the science is astonishing. By learning and sharing, we become better prepared. Science is the key to a safer future.